This lecture is going to be over section 29.4. We'll talk about the structures and properties of solids. So a crystalline solid is characterized by long-range order, a recurring pattern of atomic positions that extend over many atoms. Liquids can have short-range order, but not quite the long-range order that you see in solids. We can understand many macroscopic properties of solids, including mechanical, thermal, electrical, magnetic, and optical properties by considering their relationship to the microscopic structure of the material. So you can see a face-centered cubic molecule. You can see a body-centric cubic molecule. So condensed matter includes both solids and liquids in both states. The interactions between atoms or molecules are strong enough to give the material a definite volume that changes relatively little with applied stress. The distances between centers of adjacent atoms or molecules in condensed matter are of the same order of magnitude as the sizes of the atoms or molecules themselves, typically 1 to 5 or 0.1 to 0.5 nanometers. Crystalline structure, or solid, is characterized by long-range order, which is a recurring pattern of atomic positions that extend over many atoms. This pattern is called the crystal structure or the lattice structure of the solid. Four examples of crystal lattices are shown here in the figure. Most liquids have short-range order, correlations between neighboring atoms or molecules, but not long-range order. These are also amorphous or non-crystalline solids, such as glass. Conversely, some liquids show long-range order, such as the organic compounds used in liquid crystal digital display devices. In some cases, the forces responsible for the regular arrangement of atoms in a crystal are the same as those involved in molecular bonds. Ionic and covalent molecular bonds are found in ionic and covalent crystals, respectively. The most familiar ionic crystals are the alkali halides, such as ordinary salt. The positive sodium ions and the negative chlorine ions occupy alternate positions in a cubic crystal lattice, like here. You can see the sodium ion here and the chlorine ion here, and so on and so forth. These forces have no preferred direction in the arrangement in which the material crystallizes, determined by the relative size of the two ions. An example of a covalent crystal is the diamond structure found in the diamond form of carbon and also in silicon, germanium, and tin. All these elements are in group 4 of the periodic table with 4 electrons in the outermost shell. In the diamond structure, each atom is situated at the center of the regular tetrahedron with 4 nearest neighbor atoms at the corners. The centrally located atom forms a covalent bond with each of the nearest neighbor atoms. These bonds are strongly directional because of the asymmetric electron distributions and result in a tetrahedral structure. A third type of crystal, less directly related to the chemical bond than our ionic or covalent crystals, is the metallic crystal. In this structure, the outermost electrons are not localized at individual atomic lattice sites, but are detached from their parent atoms and are free to move throughout the crystal. The corresponding charge clouds and their associated wave functions exist over many atoms. So we can picture a metallic crystal roughly as an array of positive ions immersed in a sea of electrons whose attraction for the positive ions hold the crystal together. In a metallic crystal, the atoms would form shared electron bonds if they had enough valence electrons, but they don't. Instead, electrons are shared among many atoms. This bonding is not strongly directional. The shape of the crystal structure is determined primarily by considerations of close packing, that is, the maximum number of atoms that can fit into a given volume. The most The two most common metallic structures, the face-centered cubic and the hexagonal close-packed structure, are shown in figure 2911. Just up that away. In these structures, each atom has 12 nearest neighbors. In a perfect crystal, the repeating crystal structure extends uninterrupted throughout the entire material. Real crystals show a variety of departures from this idealized structure. Materials are often polycrystalline, composed of many small perfect single crystals bonded together at grain boundaries. Within a single crystal, interstitial atoms may occur in places where they do not belong, and there may be vacancy, lattice sites that should be occupied by an atom but are not. An imperfection of particular interest is semiconductors, which we'll discuss in the next section. Is the impurity atom, a foreign atom, arsenic in a silicon crystal, substituting for the usual occupant of a lattice site. A more complex kind of imperfection is going to be the dislocation, in which one plane of atoms slips relative to another. The mechanical properties of metallic crystals are influenced strongly by the presence of dislocations. The ductility and malleability of some metals depend on dislocations that move through the crystal during plastic deformations. So you can kind of see how they're off center with each other. Resistivity. We can understand many macroscopic properties of solids on the basis of the microscopic structure of the materials. Electrical properties are of particular interest because of their dominant role in present-day technology. The electrical resistivity of a crystalline solid material is determined by the amount of freedom the electrons have to move within the crystal lattice. In a metallic crystal, the valence electrons are not bound to individual lattice sites, but are free to move through the crystal. Metals are usually good conductors. In a covalent crystal, the valence electrons are tied up in the bonds responsible for the crystal structure and therefore not free to move. There are no mobile charges available for conduction, and such materials are usually insulators. Similarly, an ionic crystal such as NaCl has no charges that are free to move, and so a solid is an insulator. However, when it's melted, the ions are no longer locked into their individual lattice sites, but are free to move, and molten salt is a good conductor. There are, of course, no perfect conductors or perfect insulators, but the resistivities of good insulators are greater than those of good conductors by an enormous factor. The resistivities of all materials depends on temperature. In general, the large resistivity of an insulator decreases with temperature, but that of a good conductor usually increases with increased temperatures. Two competing effects are responsible for this difference. In metals, the number of electrons available for conduction is nearly independent of temperature, and the resistivity is determined by the frequency of collisions between electrons and the positively charged ion cores in the lattice. As the temperature increases, the amplitude of the vibration of the ion core increases, and the electrons collide more frequently with the iron cores. This causes the resistivity of most metals to increase with temperature. In insulators, the small amount of conduction that does take place is due to electrons that have gained enough energy from thermal motion of the lattice to break away from their home atoms and wander through the lattice. The number of electrons able to gain this much energy is very strongly dependent on temperature. A twofold increase in the number of mobile electrons for a 10 Celsius degree rise in temperature is typical. Partially offsetting this energy gain is the increased frequency of collisions at higher temperatures, as with metals, but the increased number of carriers is a far larger effect. Resistivities of insulators invariably decreases rapidly. Electrical resistivity or conductivity is closely related to thermal conductivity, which involves the transport of microscopic mechanical energy rather than electric charge. Wave motion associated with vibrations of the crystal lattice is one mechanism for energy transfer. In metals, mobile electrons also carry kinetic energy from one region to another. This effect turns out to be much larger than that of the lattice vibrations, and as a result, metals are usually much better than thermal conductors than are nonmetals, which have fewer free electrons. Good electrical conductors are nearly always also good thermal conductors.